Now, if f of x was your original graph, f of x are the y values on your original graph, when you're doing the reciprocal, it's a rather simple idea. The only thing that happens is you change your previous y values to 1 over y. And this is like, if I wanted to stop teaching here, I could just say, okay, now go play with that and see what happens. But a lot of weird things kind of happen when you do this, and a lot of shortcuts that we can use to make this easier. But this is the simple, if I take out my highlighter, that's the simple rule. It just changes your previous y values to 1 over y. So if you had the point 3 comma 5, if you had the point 3 comma 5, you now would have the point 3 comma 1 over 5. But there are some special things that happen. So we're going to look at how we go about graphing this. You're going to graph your original graph first. So whatever the bottom was, if it's a parabola, graph a parabola. If it's a sine graph, graph your sine graph. You draw the bottom first, and then you're going to look, and wherever your original graph had x-intercepts, you're going to get vertical asymptotes. Why? Because if you had a point 3 comma 0, and then your y value changed to 1 over, you have a non-permissible value. Non-permissible values we learned in chapter 2 are either going to be vertical asymptotes or holes. And in this situation, they will always be vertical asymptotes. So when we go to graph, and we're going to do some examples that are going to go through this, that's going to be one of the main things. Next, you're going to look if there's going to be a horizontal asymptote. And anytime your y values get really, really big, when you do 1 over a really, really big number, it gets close to 0. So anytime my original, well, that's yellow. So let's say I had a parabola. And my parabola looked like this. Well, step 1 would say, here and here you have x-intercepts. Those will become vertical asymptotes. And then step 2 says, if your end behavior goes up forever or down forever, that means your y values are getting bigger and bigger and bigger and bigger. If they get bigger and bigger and bigger, that will mean that you have a horizontal asymptote at y equals 0. Because eventually it's going to be a billion. And then your new y coordinate is 1 over a billion, which is really, really close to 0. And it will just keep getting closer and closer to 0. Sometimes, as far as my memory goes, I actually put step 2 and 3 together, and I just say, do all of your asymptotes. Vertical asymptotes, where you have x-intercepts, and a horizontal asymptote at y equals 0, if your original graph has an arrowhead going up forever or an arrowhead going down forever. So I sometimes just sort of like to make things easier, step 2 and 3, I just think asymptotes. Then I actually put steps 4 and 5 together. And if you want to write this beside 4 and beside 5, just do some nice points. If you have the point 2 comma 4 on your original graph, you're going to have the point 2 comma 1 over 4. So if I would look back at the mini parabola that I just drew, if I knew on the blue graph that I had the point 0 comma negative 4, I would know on my green graph, on my reciprocal graph, I would have 0 comma 1 over negative 4. Your y value just goes on the bottom. So as many nice points as you can do, draw them, right? Like over here in this section, maybe I had 4, 5, I don't know. So then on my reciprocal graph, I would have 4, 1/5. It's that easy for the y values. Whatever your original y value is, you just do 1 over that value. Now, if, and like step 4 and 5 go through some specific things, they say if you have y values of 1 or -1, they're not going to change, right? Because you do 1 over 1, you still get 1. If you do 1 over -1, you still get -1. So these are called invariant points. It will be, if I go back to the graph here, and I said, here is 1, and here's here's 1, and here's -1, then my green point will be exactly the same as my blue point at those sections. I don't even need to know what the x coordinate is. Where my y value is 1 and where my y value is -1, they're going to be invariant points. We had invariant points on our square root graphs too, right? At 0 and 1. This one we have invariant points at 1 and -1. Right? Step 4 is nice points. Step 5, you can write nice points there too. The bigger your value is, when you do 1 over, it becomes the smallest value. So maximums become minimums, minimums become maximums when you do the reciprocal. So steps 4 and 5 is just going to be about doing nice points, and just like in chapter 2, you know how I said your asymptotes in chapter 2, I said, oh, this asymptotes make 3 sections for you, right? And you had to find at least 1 point in each section. It's going to be very similar. In fact, the 1 over f of x is very similar to our rational graphs that we did, except now f of x on the bottom could be a log graph. It could be a sine graph. It could be an e to the x graph on the bottom. So once you have, and final step, step 6, is once you have your nice points, you have your asymptotes, your final graph, it's going to go through your nice points and approach your asymptotes just like we did in chapter 2. So there's a lot of connections between our rational graphs going towards the asymptotes. These reciprocal graphs will also go towards your asymptotes. The other thing about a 1 over f of x graph is since the top is 1, your reciprocal graphs will have no x-intercepts, with the one exception of cotangent, but we'll get to that when we get there. So that's what step 6 says. We just draw the graph towards the asymptotes once we have nice points in each section. Now, I have handed out to you these examples. They have all of the steps drawn out step by step for you. All the work is shown, but I'm going to do them with you how you would do them, okay? So usually what's going to happen is if you're asked to graph 1 over x squared minus 4, you would draw the original, which is right here. Wow. I'm trying to draw it. I won't. I'll just draw it proudly. So, I'm struggling with the asymptote. And on here, I've labeled my minimum 0, -4. I have x-intercepts at 2, 0 and -2, 0. And I could find more points if I wanted to, right? I could plug in 1 and I would get 1, -3. I could plug in 3 and get 3, no, close. If I plug in 3, I'd get 3, 5. And similarly over here, I get negative 3 comma 5. So I have my original graph, and then right beside it, I would start graphing my reciprocal. Step 1, figure out all of my asymptotes. Do I have any x-intercepts? Yes, I have an x-intercept at 2. Right, at 2 and negative 2. Does my graph have arrowheads that go to positive infinity or negative infinity? Yes. So I would also draw my asymptote at y equals 0. In my head, I think step 1, I'm going to do all my asymptotes. Sometimes if you combine steps, it makes it easier to remember because then you don't have as much stuff to do. So there's all my asymptotes. After asymptotes, get as many nice points as possible. So look at my original graph. I've got 0 comma negative 4. What's going to happen to that point? 0 comma 1 over negative 4. I have 1 comma negative 3. What's going to happen to that point? 1 comma 1 over negative 3. I had 3 comma 5. 3 comma 1 over 5. And negative 3 comma 1 over 5. I just did a bunch of nice points. Do I have a point in each section? Yes. This is enough. Draw towards the asymptotes. Your graph should have no x-intercepts. You're done. Okay? This graph you did in grade 11 pre-calculus. You did the last chapter in grade 11 pre-calculus for grade 11 did reciprocals of lines and parabolas. In grade 12, we do lines, parabolas, and anything else. But it's exactly the same logic that you did in grade 11. So this is a bit of review. And in grade 11, I gave names to each of the parabolas when you do this. I think I called this one a sad clown face or something. It's kind of got a frown.
Batman.
No, the Batman's the other way. This one's sad. You did the flip of this one, definitely Batman. We'll see which other ones I've got going. Okay. Here, 1 over x squared plus 1. Ooh. We get the official graph of Manitoba with this. No, this isn't the official graph of Manitoba. It's not the pothole. This is the speed bump. So you have your original graph. Look at the points we've got. 0 comma 1. We would have 1 comma 2. We would have 3 comma, I'll do 2 comma 5. And over here I'd have negative 1 comma 2 and negative 2 comma 5. Then right beside it, I would do my reciprocal. Do I have any x-intercepts? Because step 1, do all your asymptotes. There are no x-intercepts, so this one has no vertical asymptotes. However, does it go up forever? Yes. So there's still a horizontal asymptote at y equals 0. Next, do your nice points. What's going to happen to 0 comma 1? It's going to be an invariant point and stay 0 comma 1. 1 comma 2, 1 comma 1 over 2. 2 comma 5, 2 comma 1 over 5. And over here I'd have negative 1 comma 1 over 2. And negative 2 comma 1 over 5. If I connect those points and go towards my asymptote, I get the speed bump graph. Yeah, if the parabola was underneath, you'd get the pothole one, which is the official graph of Manitoba. Yes. So again, I wrote out all the steps separately, but in reality, you would just graph your original and then go right away and do all of your steps on the other one at the same time. So now we'll do one. Oh, here. Yeah. Now we'll do one that is a graph from this here. So on the bottom, you have the square root of x plus 4. Here's your original graph. It's just a square root graph moved 4 to the left. Then right beside it, we'll start with asymptotes. Do we have an x-intercept? Yes, at -4. So at -4, I'll have a vertical asymptote. Does our graph go up forever? Does the square root keep going up or does it flatten out eventually? It just keeps going up. So we will have an asymptote at y equals 0. Next, nice points. I have -3, 1. It will become -3, 1 over 1, which is an invariant point. I have 0, 2. That'll become 0, 1 over 2. Now our asymptote splits our graph up into 2 sections, but do you see on the original graph there is nothing to the left of -4? So does it make sense that there should be nothing to the left of -4 on our graph as well? When we go to graph this, this is it. I came very close to an E10 error on my graph. One on the left side almost looks like I go through it, doesn't it? I got a little bit lazy there. Is it almost touching the asymptote instead of getting closer to it? And then on the right side, is it coming up a little bit? This would be a dilemma for the marker. They'd be like, is that enough to take off the E10 error? Yeah, you're like, Jesus, like. Lots of times on the final exam, you'll get questions like this. They'll give you the random graph and ask you to graph 1 over f of x. Okay. So they gave me the graph, and I have to draw the reciprocal graph. So I start with asymptotes. Are there any x-intercepts? Yes. There's an x-intercept here, here, and here. So at -2, no, that's wrong. -1, thank you. I was already looking at this one. This one's at 2. And then 1 at 3, 4, 5. Wait a second. You might did that. 3, 4, 5. Here we go. X equals 5. On the left-hand side, it does not have an arrowhead. Okay? But on the right-hand side, it does have the arrowhead going up forever. If there was no arrowheads, there would be no horizontal asymptote at y equals 0. But there is an arrowhead. Right? So So we have a horizontal asymptote at y equals 0. Does it make sense that horizontal lines, they always have the same y value, right? So when you do a reciprocal of them, if they were always at 2, your reciprocal would be always at a half. These ones are always at 1, so I'm going to have 1, 2, -5, -1, -2, -1. This is going to stay a flat, straight line on my reciprocal graph as well. 0, 1 is a nice point. It's going to stay 0, 1. 4, -1 is a nice point. It's going to stay 4, -1. And 6, 1. Boy, there's all invariant points labeled like crazy here. So I labeled a bunch of nice points and I labeled that straight line. Now we have to go towards asymptotes. Okay? Section 1 here. Careful not to put an arrowhead to the left. Our original graph stopped at -5. Our graph stops at -5. But as we go to the asymptote that's x equals -1, you have to decide, are you going to go up or are you going to go down? And we have to go down. Ooh, I know. Okay, touch the reference. That's better. It has to go down because if it went up, you would get an x-intercept. And 1 over graphs don't have x-intercepts because the only way they equal 0 is if the top was equal to 0 and your numerator is 1. So that kind of tells you here too, I know that this has to go up towards the asymptotes on both of those sides. And this section here, down towards my asymptotes. And this up towards my asymptote, and here it does have an arrowhead, so it's going to have an arrowhead on the right. So once we have our points, then we just need to graph things towards our asymptotes. So this is a very typical, they give you a picture and they ask you to draw the reciprocal on the exam. They really like on the exam giving random pictures and asking you to do any sorts of transformations. Could you move it left and right? Could you stretch it or press it? Could you do the square root? Could you do the 1 over f of x? Eventually we'll do the absolute value of f of x. We'll do that tomorrow probably. If you want some practice with these, here is a worksheet. Again, I took exactly the same amount of 2 feet. So next, we're going to do reciprocals of trig functions. And I've got these notes for you as well, so you don't have to write stuff down. So reviewing our trig unit. You know that cosecant is 1 over sine. So if we wanted to graph cosecant, we could just graph 1 over sine. And graphing 1 over sine, we just draw sine first, and then do all the steps for reciprocals. So here's our graph of sine. Step 1 was asymptotes. Do we have x-intercepts? Lots of them. So we're going to have, like, oh my goodness, look how many x-intercepts. I should have drawn less of the sine graph. But wherever those are, if you don't put arrowheads on asymptotes, they actually don't take off marks. But I'll put them on. If you draw your asymptotes with solid lines, they do take off marks. Or if it's squiggly, but not dotted, they take off marks. Do we have an asymptote at y equals 0? Does our graph go up to infinity or down to infinity? No. So we don't need to draw a horizontal asymptote on this one, because it stays between 1 and -1. Do we have some nice points? Well, right here, we have pi over 2, 1. When you do the reciprocal, you'd have pi over 2, 1 over 1. It would stay the same. Does it make sense that all of these maximums at 1 are going to stay the same? I mean, you could do another point, like on my original graph here, I have pi over 6, sine of pi over 6 is a half. So on my green graph, I would have pi over 6, 2 over 1. The reciprocal means you just take the fraction and flip it. Or you could write 1 over a half, which is dividing by a fraction, multiplied by the reciprocal, you'll get 2 over 1 anyways. And same thing where it's -1. 1 over -1, all of those points will be invariant points as well. And your cosecant graph looks like this. So I'd like you to try the secant graph, the next one, on your own. So this is the formula for intensity of sound. Okay. They've told you hockey game was 115, so the intensity of hockey game was 115. Or that is the decibels, right? Yep, the decibels, 115 for the hockey game. And 90 for the other one. So you're going to need to solve for I. In one equation I do IH for hockey game, and the other one I would do I. Bus. Truck. IT for the other. So if you plug in the 150 would be there. It's 10 log I H and I0. I0 is like a constant. Like the constant is the track. eyes, your nose, like they have a very small sound that they measure everything on. Now, can you get the IH by itself? Divide by 10, change to exponential form, and solve. It'll be very similar to comparing earthquakes. Once you've got IH by itself and IT by itself, you divide the two. Yeah. No, dotted is fine, as long as it's not like squiggly with you. Oh, this is good. All right, let's see how you did. Did you notice that the secant graph looks very similar, just like sine and cosine graphs are very similar? The secant and the cosecant graphs are very similar. We have a bunch of asymptotes. All of the minimums are invariant points. All of the maximums are invariant points. And the trickiest reciprocal one is cotangent graph. It is true that cotangent is the reciprocal of tangent. Okay? It is also true from our identities unit that cotangent is cos theta over sine theta. The graph of cos theta over sine theta is slightly different than the graph of 1 over tan theta. In the graph of 1 over tan theta, you would have no x-intercepts because there's a 1 on top. But in the graph of cotangent being cos over sine, wherever cos is 0, that fraction is 0. So we're going to use the tangent graph to help us graph cotangent, but in reality, mathematicians use cos theta over sine theta as the actual graph. So we're going to see how that makes a difference. I've started by graphing tangent. And so wherever tangent is 0 is exactly the same place where sine is 0. Sine and tangent are 0 at 0, pi, 2 pi, 3 pi, 4 pi, and the same thing in the negative direction. So at each of these, we're going to draw vertical asymptotes. And this is where the cotangent graph has the exception. Normally, you would draw a horizontal asymptote at 0 because the tan graph goes to infinity. But in the cotangent graph, we don't because we use the blue that it's cos over sine, and cos is equal to 0 at pi over 2, 3 pi over 2. In fact, cos is equal to 0 everywhere where tan has an asymptote. Because if we think about tangent, right, from our identities unit, tan of theta is also sine of theta over cos of theta, does it make sense that the tangent graph has vertical asymptotes wherever cos is 0, because that's the non-permissible values for tan? And if you think about your pi plate, your unit circle, it's not possible at pi over 2 and 3 pi over 2. And at pi over 2 and 3 pi over 2, that's where cos is 0. So this is where the cotangent graph is a little bit different. Instead of having an asymptote at y equals 0, you have x-intercepts wherever the tangent graph had non-permissible values. Because the non-permissible values of tangent are now in your numerator, and they are the x-intercepts of cotangent. Now, as far as finding nice points, you know that tan of pi over 4 is 1. And that would be an invariant point. In fact, I would just go across from 1. And wherever the graph hits 1, I draw a dot. Those are my invariant points. Same thing with -1. Wherever my graph hits -1, I would graph a point. With those 3 points and your asymptotes, you have enough to draw your cotangent graph. Your cotangent graph has a very similar shape to your tangent graph. It just is going in the opposite direction. So the cotangent graph is a little bit complicated. Statistically speaking, it's shown up once every 10 years on the exam. Not very often, but it has shown up. So you do need to know it just in case you're the lucky year that has the cotangent graph on there. But cosecant and secant are much more likely to show up.